And welcome to a video going over the study review guide for Ecology Unit 1. I know my handwriting isn't always the best, so I want to just go over some of these questions. So this first question, thinking about analyzing data sets based on averages or standard deviations, population 1 does grow faster because if you take the average, should say population 2, 130, and add the 30, which is plus or minus for the standard deviation, that means that population could have up to 160 births per year on any given year. Now, population 1, I'm sorry I mixed these two up, is way more consistent. Its range is between 90 and 110, and that's because its standard deviation is only plus or minus 10 compared to the average. So standard deviation really tells you the measurement of accuracy of a group of data when you compare it to the average. Plus or minus 10 is going to be a lot more accurate and precise compared to 100 versus 130 and 30. This is 3 times more wiggle room, more variance, more error than the other population. When it comes to calculating growth rate, remember it's the Biden rule. You add births and immigration and subtract deaths and emigration, which gives you a 20 total gained, which is our net, which means our new population is 350 plus 20, which is 370. To get percent, you do the new population minus the old population and divide by the old population, multiply that by 100. So we're adding about 5.7% of our total population with that new addition of 20. When it comes to analyzing scatter plots, the trend line is going to be showing you the general trend of the data, and this is a logarithmic trend line, which means over time, the rate of change gets less and less. Our R squared is 0.336, which means 33% of our data, which is the change in a potato mass, is related to the saline concentration or the saltiness of our environment. I see some really imprecise data here because for the same X variable, I have all of these different Y outcomes. So imprecise data is when you have one specific X variable and you get a lot of different results. These 3 groups right here are precise, but notice they are not hitting the trend line. They are all being underestimated. And then over here, I see really precise data that does fall in the trend line, which means it's both accurate and precise, and it is well represented by our change. So the clumping of data is really important for us to understand whether or not the data is good or bad, precise or imprecise. When it comes to determining soil types, you always do clay across, silt down, and sand up, and that gives us basically a clay loam. And because clay is greater than sand in this soil by 5%, it's going to be not as acidic than if sand was the more important part. It will retain more water. It will do well in the summer because it won't overheat, it won't dry out, but it could become waterlogged. When it comes to looking at the red maple in terms of where it thrives, we have these niche maps, which is showing you all of these forests plotted on a scatter plot. And I drew a box based on the min and max value for precipitation and temperature that contained most of the blue data points, where the maple tree is thriving. So if I look at these Y and X values for temperature, the best range is between 41 or 42 and 52, which is about an 11 degree Fahrenheit. If I take 41 and divide it by 52, the minimum temperature that maple trees thrive in is 80% of the max. This is showing me a pretty restrictive range because the min and max are so close to each other. For rainfall, it's about 30 to 60, which is a range of 30 inches. It's a little bit broader. And if you take 30 and divide by 60, it's about 50%, which means the min and max are further away. Maple trees, for their ideal condition, have a wider precipitation range. Now, if you look at this graph in its entirety, maple trees can survive in far greater amounts of temperature, 36 all the way up to 77, but I'm really analyzing this graph based on where maple trees thrive. And when I look at where they thrive, they do far better in a restrictive cold environment than a rainfall. What I did for this, where I looked at predictor maps and compared it to importance values, is I circled the areas where I saw lots of blue and then circled those same areas on this predictor map, and I saw that maple trees generally thrive best when rainfall is between 900 and 1300 millimeters, which does match what I saw up here, in that maple trees don't like it not dry, but also not too wet. It's somewhere in between. I do know that rainfall isn't the only important predictor, because if I go over to Wisconsin and Michigan, I see a good amount of blue and the rainfall is really low. And if I go down to the south where the rainfall is quite high in that range, there are no maple trees. So again, there's a variety of reasons why trees will exist in one location as opposed to another. But this is showing me a pretty good relationship between moderate amounts of rainfall and where the red maple trees are. For calculating efficiency rate, you always take the energy available in the trophic level below it and divide by the trophic level in it. So if I have 100 million joules of energy in sunlight hitting a forest, but the plants only contain 950,000 joules, I'm going to take 950,000, divide by 100 million, and that gives me 0.95%, or roughly 1%. When I do 73 to 950, I get 7.8, and 8,000 divided by 73,000 is 10.9%. When we look at the lynx and hare peaks, all you need to do to calculate average peaks is take the individual peaks, 90, 110, for hare, divide by 9, which is about 98 to 100,000. And then the same with the lynx, 57,000. And why is there this delay? The only way that a lynx population can grow is if the hare population grows before it. And as soon as this lynx population gets quite large, the hare population is going to plummet, which will then cause the lynx population right afterwards to plummet as well. So this is showing the prey-predator dynamics, where for one population to grow, the other population has to be big. And as soon as that other population gets small, so too will the other population. When I look at Stow's climograph, I know that Stow is in the northern hemisphere because we get more rain and we have hotter weather in May, June, July, August, September. Our summer months are during the months where the northern hemisphere gets more sunlight. And I know that we're pretty close to a body of water because we get pretty consistent amounts of rain throughout the entire year. If I put Stow up higher in elevation, that would cause the rainfall to decrease because air temperature, when it gets colder, is always going to hold less rain. And also our temperatures would generally get colder as well. Okay, in terms of content, abiotic conditions are non-living. Oh, I pointed these to two different ones, so sorry about that. Food, mates, community, symbiotic relationships like the pikas and the marmots are all biotic factors. Abiotic factors like shelter, oxygen, water, temperature, calorie, space are non-living. A niche generalist has a broad set of living conditions away from the average or the ideal condition. They can do well in a lot of conditions. Niche specialists need specific requirements. Their range of available habitat is really close to the average or the ideal. Competition between species or individuals of the same species is always bad. It means more energy is wasted on acquiring limited resources. This is why when we look at tree data or species data, most species have specific distinct niches to specialize in one particular thing that will minimize their competition. In terms of the three types of dispersal, we have a uniform, which is when species are territorial and have very specific niche requirements. We have random, which is for generalists that have no territory requirements. They can grow wherever. And then we have clumped, which is when individuals all gather because they have social and protection requirements, or they're sharing resources like limited water, limited food. They need to create a community. When you go further away from the equator for temperature, it's going to generally get slower, it will get colder, and it becomes more inconsistent or more variable. Temperature is always really hot and consistent near the equator. Rainfall is always going to get less when you move away from the equator because there's less evaporation. Temperatures are always colder at higher elevations, and rainfall always decreases with higher elevations, and that's because colder air holds less water. When we're close to a water body, like a lake or an ocean, temperatures are almost always warmer, and they're more moderate because water acts as a heat sink and buffer. When we're close to a body of water, rainfall always increases, and it always means that we have higher levels of precipitation. The CEC is the cation exchange capacity. It's how many positively charged molecules like magnesium or sodium or aluminum is held in the soil. It's basically a nutrient measurement. Clay increases the CEC. Sand, because it's acidic, holds a less CEC, so sand is generally bad for soil health. NPP is just the total amount of calories made by plants for animal energy and consumption. It's like your paycheck. How much money do you have to spend on fun things? When we eat food, the energy and matter is first converted into heat and energy to keep us alive, waste products, and then finally new growth or biomass. Exponential growth is when over time the population grows rapidly at a nonlinear rate. Logistical growth is when the population slows over time as it reaches its carrying capacity. When you look at type 1, 2, and 3, type 1 species have most of their babies survive adulthood because they have few babies with lots of care. With type 2, the births are equivalent to the deaths throughout their life cycle. And type 3 species have lots of babies, so most die early in their life. R-selected species grow fast. They generally have more births than deaths. K-selected species often show logistical growth. They grow slow because the births equal the deaths. Most humans grow K-selected because we have two babies. For two parents, the replacement rate is basically the same. Density-dependent factors that limit growth as species get bigger in terms of their population could be food, space, competition, disease. The more individuals there are, the more these things matter. Independent factors are disasters, storms, weather events that affect all populations regardless of their size. I hope this overview has been helpful. Obviously, feel free to ask me questions on Friday about any of this. I hope this will help.